Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about mass transfer theories. There are various theories in mass transfer. The first theory is film theory in the mass transfer. The second theory is penetration theory, film theory. The second theory is penetration theory. Penetration theory. The third theory is surface renewal theory. The fourth theory is the boundary layer theory. In this lecture we will discuss about the film theory. It is the film theory in the mass transfer. So suppose we have a solid surface. This is a solid surface, and suppose there is a liquid attached to the solid surface having thickness delta. This is the thickness of this is the solid surface. There is a liquid which is stagnant, which is stationary liquid, which is attached to the solid wall. This is the stationary liquid. This is the thickness. Delta is the thickness of the liquid. And there is some fluid flowing. This is turbulent fluid. This is turbulent flow of some fluid, can be gas or can be liquid. This can be turbulent flow. Of fluid, which can be gas or liquid. Suppose it is liquid. Now the concentration of solid, the solid is slowly and gradually dissolved in the liquid. The solid molecule transferring in the stationary liquid. This second, the solid is dissolving in the liquid. First of all, it passes through this thickness delta, and then it come out to the bulk liquid, where it is transferred to other place by convective mass transport. So this is a solid surface. You know, this is a solid surface. So the concentration of component A, suppose component A is dissolving into the liquid having thickness delta, and when the component cover the thickness, then it come out to the turbulent flow, and then it carry away by convective mass transport phenomena. So the solid having this is a solid surface. The component A is dissolving in the liquid. So the concentration of component A at the surface is, suppose it is a CaI. The concentration of component A in the bulk is CaB. Concentration of A in the bulk is CaB. This is the Z direction. This is the is the z direction. This is the z direction. This is the z direction. The mass is transferred in the z direction only. That is one directional mass transfer procedure. So suppose we consider a small element of volume. Suppose we consider a small element in this layer, in this stationary liquid layer, having thickness delta. So this is a small. This is the thickness of the thickness. This is a small element. Element having thickness delta z. Delta z. This is the z direction. This is the z direction. Now this is the z direction, and this element is normal to the z direction. The area normal to the z direction is this area. This area is normal to the z direction. Suppose for simplicity we will write it. Suppose we consider an element of thickness delta z, which is normal to the z direction. This is the z direction. Now the component A is passing through this small element at z position is NAZ. Suppose this is the z position. So the flux of A at the z position is NA at z position. So the flux of A at z position is NAZ at this position. Similarly, the flux of A at z plus delta z position is this at this position. This is z plus delta z. This is z position. This is z position. So the flux of A at z plus delta z at this position is NA z plus delta z. Z plus delta z. Z plus delta z. Now we will derive equation for the transport of component A in the z direction. So we consider a wall. This is concentration of component A at the surface is CAI. This is the thickness of the stationary liquid layer. This is the bulk. So in the concentration of A in the bulk is CAB. This is the bulk liquid. The component A only transfer in the z direction. The z direction, we consider a small element. So flux of A in the flux of A at z position is NAZ. Flux of A at z plus delta z position is, this is z position, and this is z plus delta z plus delta z position. So the flux of A at z position at this position is NA at z. Similarly, the flux of A at this position is NA z plus delta z. So from material balance we know that input material minus output material plus generation of material minus consumption of material is equal to accumulation of material. So there is some assumption for the film theory. The first assumption is that it is a steady state process. The component A is flowing to the transfer to the liquid, but this process is a steady state process. So the steady state process. So steady state definition term is 0. The second assumption is that only the molecular diffusion process, molecular diffusion are taking place in the film theory. Only molecular diffusion are taking place. Only molecular diffusion are taking place. This is the second assumption. It means that the convective mass transport term, which is Na plus Nb into Ca divided by Ct, this is the convective mass transport term. This is so we assume that this term is 0. Only diffusion are taking place in the z direction. So this is the assumption of the film theory. So there is no generation, no consumption. So these terms are also 0. So input minus output is 0. Input minus output is equal to 0. Input minus output is equal to 0. The input was, this was small element, flux of A at the z position, and this is the delta z thickness, the small element, the delta z. This is the thickness of the small element delta z, and the flux of A at this position is Na z plus delta z. The flux of A at this position is Na z plus delta z, and the flux of A at this position is Na z, which is this flux. So this is the input, and this was placed in stationary near hand thickness, and this was the bulk flow, and the concentration of A in the bulk was CAB. This was the concentration of A at the surface. This is the z direction. When z is equal to 0, the concentration of A is Ci. Similarly, when z is equal to some value, when z is equal to sigma, then the concentration of A will be Ca. These are the boundary conditions. We will discuss this in this lecture. So this is the input, and this is the output. If we consider this small volume in the stationary liquid layer, so input is Na z minus output is Na z plus delta z. So the component A entering to the volume at z position is Na z. The component A come out from the small control volume is Na z plus delta z, which is equal to 0. Now suppose this is equation 1. Now divide equation 1 by delta z and let delta z tend to 0. Now decrease this delta z to very small, so it will give us the definition of first order derivative, which will be equal to d by dz into Na minus Na is equal to 0. So we derive equation for the flux of A, which passes through the small element having thickness delta z. So minus d by dz Na is equal to 0, or d by dz Na is equal to 0. Now we know that the flux of A is equal to Na plus Nb. The total flux of A is the sum of flux, so the total flux is equal to the flux of A due to convective transport plus the flux of A due to conductive or molecular transport of A. So this is the convective term, Ca by total concentration, and this is the minus dAb, diffusivity of A and B, dCA in the concentration of A which changes in the z direction. So there was assumption that this term is 0. So NAZ is equal to minus DAB dCA by dZ. So NAZ. So putting suppose this is equation number, suppose this is equation 1, this is equation 2. Put equation 2 in equation number 1. So we will get d by dz dAB dCA by dZ in the minus term. This is the minus term. So equal to 0. So d is, there is also assumption that diffusivity of A and B is equal to constant. This is also, as we also assume the diffusivity of A and B, dAB is constant. So dAB is constant, it come out from the differential sign. So dAB, so this equation will be equal to dAB d by dz dCA by dZ into 0. This minus sign come to the right side and it becomes 0. So this is the equation. Suppose this is equation number 3. So dAB, from equation 3, dAB d by dz dCA by dZ is equal to 0. Further simplify d by dz, divide both sides by dAB. This term will be come to this side dAB and it will be equal to 0. So d by dCA d by dZ is equal to 0. Now further simplify dCA dZ is equal to 0 into dZ. So d into dCA by dZ, this is 0. Now suppose this is equation number 4. Now integrate both side equation of equation 4. So we will get, now after integration we will get into dCA by dZ. Take integral sign equal to 0. Take integral sign, as you know the integral of 0 is constant, and this cancel with this. So dCA by dZ is equal to constant. So dCA, the final equation is dCA by dZ is constant. C. Now further simplify dCA by dZ, dCA is equal to C and constant into change in z direction. Now take the integral of this equation. So suppose this is equation number 5. Take integral on both sides of this equation. So we will get constant will come out from the integral. So it will be C into dZ. This is the dCA. So as we know that there was a stationary wall, this was the thickness, of the stationary liquid, there was a bulk flow, this was the z direction, mass was transfer was in the z direction, and the concentration of A, at z is equal to 0, concentration of A was CAI, which was the boundary concentration. Similarly, when z is equal to sigma, this sigma, so when z is equal to sigma, the CA will become CAB, given. So now we know that dCA is equal to C into dZ. Take integral sign on both sides. This is the constant, it will be come out from the integration dz dc a. Now this is the this is the when z is equal to when z is equal to 0, suppose this is the thickness of the stationary liquid layer, concentration of A is CaI when z is equal to 0. This is the z, this is the bulk, concentration of A is Cab, this is the bulk liquid thickness. Now when z is equal to 0, at this place concentration of A will be CaI. So let's simplify this equation. Suppose this equation x, so it is nothing but Ca minus Ca1. Suppose this is Ca1 into Ca, this is Z1, this is Z. If Z is equal to Z1, the concentration of A will be CaI. When Z is equal to Z1, concentration of A will be Ca1. When Z is equal to sigma, concentration of A will be Cab, concentration of A in the bulk, which is Cab. So simplify equation x, this equation. So Ca minus Ca1 is equal to constant of integration z minus z1. Now when z1 is equal to 0, suppose this is z1. Suppose first of all, at first this was z1 point. Now when z1 decrease, suppose when z1 is equal to 0 at this position, when z come to this position, then the concentration of A will come to CaI. So the Ca1 will be equal to CaI. Now when z is equal to z1, then the Ca1 will be equal to CaI. So when z1 is equal to 0, the concentration of A, the Ca1 is equal to CaI. So Ca minus CaI is equal to C into Z. Now similarly, this is the first boundary condition. Similarly, when Z is equal to sigma, then Ca will be equal to Cab. So when Z is equal to sigma, Z is equal to sigma, the constant of integration, then this Ca will be equal to Cab, and this is the CaI already given. So two equations, one is equation A and equation number B. Divide equation B by equation A. Ca minus Cai, Cab minus Cai. So from equation A and B, which is Ca minus Cai, is equal to C into Z. Z. Equation B, this was equation A. Equation B is Cab minus Cai equal to C into sigma. Equation 2. Now divide equation B by A. We will get, divide this equation by this. Let's cancel with this. There's nothing but Ca minus Cai divided by Cab minus Cai is equal to Z divided by thickness of the stationary liquid layer. Further simplify, Ca minus Cai is equal to Cab minus Cai into Z divided by sigma. So Ca minus Cai is equal to CAB minus CAI into Z by lambda. So this is the linear equation. This equation is a linear equation. It shows us that the concentration decrease linearly in the stationary liquid layer which is attached to the solid surface. So this equation is Ca minus Cai is equal to Cab minus Cai into Z. This is the thickness of the stationary liquid layer in this is the Z direction, this is the thickness of the stationary liquid layer. So Ca minus Cai is equal to Cab minus Cai. So Ca minus Cai equal to Cab minus Cai into Z divided by thickness. We can also write it Ca is equal to Cai minus Cai minus Cab and to Z divided by thickness of the stationary layer. So this is y is equal to C minus n into x. So it is just like straight line. The constant y-intercept is slope. This is the x-axis and this is the y. So the concentration is on y-axis and the z is on the x-axis, the z direction. This is becomes Ca and this is the thickness. This is the slope. This whole is the slope, and Cai is the y-intercept. So this is the y-intercept Cai, and this can form slope like this. So minus this is the slope of the line. So in this case the concentration decreases in the z direction, which is shown by this equation number C. Suppose equation number C. So Ca is equal to Cai minus Cai minus Cab into Z divided by lambda. Now we can further simplify this equation to find the flux of A in the Z direction. So we know that Ca minus Cai equal to Cab minus Cai into Z divided by sigma, or Ca is equal to Cai minus Cab into Z divided by thickness of the stationary layer. Now we know that flux of A in the Z direction is nothing but minus dAb dCA in the Z direction. This was equation C. Now differentiate this equation C with respect to Z direction. So it will give us dCA. So from equation C we will get dCA by dZ, which is nothing but it will be equal to minus this is constant, so it will be 0. Constant of the derivative is 0. Derivative of constant is 0, so this will be equal to minus Cai minus Cab divided by thickness. And with the Z direction, this Z will be also cancelled, because we know that dZ with Z direction will be equal to 1. So now dCA by dZ is this number. Now multiply suppose this equation D, multiply equation D by minus DAB multiply this side by minus DAB, also this side by minus DAB. Minus and minus will be cancelled, so AB and this is the D, which will be equal to DAB, and this is nothing but A. So the flux of A in the Z direction will be equal to minus dAb dCA by dZ, which will be equal to diffusivity of A in the B divided by thickness, this thickness M to Cai minus Cab. This is the this is the gradient, this is the concentration gradient, and this is the resistance to the gradient, this is the thickness, this is the resistance to the gradient, and this is the flux of A in the Z direction. So dAB divided by thickness is nothing, but it is just like the mass transfer coefficient, as we know that NA Z is equal to KL CA I minus CA B. Sorry, NAZ, we know that NAZ is equal to KL CAI and CA B. Suppose this is equation number, suppose equation D, this is equation E. Compare equation D and E. NAZ and this case KL, this is CI minus CAB, this is CI minus CAB. So KL is equal to DAB divided by sigma, and this KL is the mass transfer coefficient. This equation is for the mass transfer. Is this for the mass transfer of component A in the Z direction? This is the mass transfer coefficient. This is the concentration of A in the interface. This is the concentration of A in the bulk. This is for the convective. This is for the convective mass transport, or the mass transfer coefficient. This is mass transfer coefficient KL. It is for the liquid. So KL is equal to DAB divided by thickness. So KL is equal to, so in this case KL is equal to DAB divided by thickness. So from the film theory, we know that the mass transfer coefficient is directly proportional to the diffusivity of A in B. But in reality, the mass transfer coefficient is directly proportional to the diffusivity of A in B to the power of some number, and this number is from 0 to 0.8. So this is some drawback of the film theory, that KL is directly proportional to diffusivity of A in B to the power 1. But in reality, mass transfer coefficient is directly proportional to the diffusivity of A into B to the power of n, where n is from 0 to 0.8. So the other theory will come which will solve this problem. But again, the film theory give us the main concept about the mass transfer, and it is very important theory. So in the coming theory, we will discuss that how the mass transfer coefficient is related to the diffusivity of A in B. So this drawback will be solved in the penetration and surface renewal theory and the boundary layer theory. So the more advanced theory will come in the coming lecture. So if you are new to the channel, please like and subscribe. Thanks.